But as Robert said, I'm a professor of geological sciences or Earth, Environmental, and Planetary Sciences at Brown University. And one of the things I'd like to talk to you about today is the Mars geology and mineralogy and how that informs our ideas about habitability. And this is not necessarily human habitability. We're talking about microbial habitability. Okay, thank you. Okay, so we're talking about seeking signs of life. And does this tell us that we actually, go ahead. Does this answer the question? Well, that was a nice Hollywood version of it. But really we're after what is the really detailed geologic evidence that there may or may not have been life on the planet. This goes back a long way. The desire there to be, having been life on the planet, to Percival Lowell and his observations of Mars turned out to be fanciful. And as we looked deeper, nevertheless it inspired the world to really think creatively from the art side, what would a Martian community look like? I particularly like this view from Gulpun, who actually had a very good idea it was a cold and icy planet, which is what we kind of think about it today. But it turns out that those creatures didn't exist. And then, of course, there was the catastrophic view that Mars were actually evil creatures coming to attack us. But of course, you know today, rather than Martians shooting us with lasers, we have the lasers shooting Mars with the Curiosity rover and the experiments we have there. But really, it's actually about the data. We actually want to see the evidence from a scientific point of view that tells us whether or not there has been the prospects of there being the right conditions to sustain life. And when we got the first data back, it was not promising. This looked kind of like the pockmarked landscape that we see on the Moon and Mercury. It wasn't promising. But with additional data, of course, maybe this is a familiar story to you all, with additional data, we realized that this planet has the ingredients from a geologic perspective to having had sustainable locations with the right ingredients to potentially have initiated a second genesis and sustain that over time. So this is really the sweet spot. This green box is meant to represent what do you need to put into place in order to have a habitable environment from a microbial point of view. So water needs particularly water, but we can't have too little water or too much. Too little, it's not going to be able to sustain. Too little will dilute it. And likewise, from a energy sources point of view, we'll get starvation with too little, and we'll burn out if we have too much energy along the way. And then in terms of nutrients, too much is toxicity. So we got to find the sweet spot. And does a sweet spot exist from an astrobiological point of view? And how do we look for that and actually direct our resources to really go after this question of there having been signs of life on this planet? So does life, or did it exist elsewhere in the solar system? How can you look at that question realistically? Would you use radio signals? I think we've done that experiment. It has been unsuccessful for this solar system. Do we use life detection experiments? Well, that presumes, actually, that the life exists there. What if you need to take the first steps rather than jump into life detection? Could you take simpler steps? How about we explore to seek the signs of life? And what were the steps you would take to do that? You would do an orbital exploration or a seeking phase where we would look with orbital spacecraft. We would get onto the surface and look at in situ, such as landers and rovers. And then, you know, the holy grail from a science perspective would be to actually bring those samples back to Earth. And we're really hoping NASA will move along with that. So this diagram I put up here to give you a sense of what's the Earth's history. What's the only place that we know where life actually got started, and where does it exist within our geologic record, and how can we put that into context to say, if you go to another planet, how are you going to look for that? So here is a circle diagram that starts with the earliest phases of the Earth at 4.6 billion years ago, and circles around in time to go to 3 billion years ago, 2.5, 2, along the way. These are the geologic eras, Hadean, Archean, Proterozoic. And then it gets a little crowded in here because now we're starting to get a geologic record that is more finely resolved. And when did life start here? Well, actually, just recently, just a few weeks ago, there was a report in our high-profile journals that said there's evidence for life at 3.7 billion years ago. And what's fascinating, climate change allowed this discovery, actually, because it's in Greenland, and due to the retreat of the ice cap, it exposed some outcrop that were able to be analyzed and said, oh, okay, so there's some good evidence in there. But that's 3.7 billion years ago, and that was not a very active form of life. Photosynthesis maybe got started. We didn't actually get an oxygenated Earth until around this time, but it was only 600 million years ago that we got the amount of oxygen that we have today, on the order of 20%, to sustain higher forms of life. Until that time, it was a pretty quiet microbial world. But I want to point out here, it took 500 million years for Earth to go from 0 to the first evidence that there may have been life. 500 million years. That's a long time. And where Earth had, it's a watery planet, so it had water on its surface for 500 million years to help kick this along. How would we go about this on the Earth? Well, one of the things is what is going to lead to life in the first place. There's a lot of theories for this. We have the primordial condensed soup from the Cambrian, Precambrian, but you need to have complex organic compounds to form this together. How do you get them concentrated? How do you get them to create membranes to separate the life component from the environment? And how do you get the DNA heredity system going? Here's a diagram of a cell group that is used to create cell walls, where you have the hydrophilic phase and the hydrophobic phase, which together come together. Now, these fatty acids have been detected within meteorites. We know it can be created abiologically. So the ingredients are there. How do you bring them together to make the systems that we want to seek as we go to Mars, as a particular example? Well, the direct synthesis of RNA is very improbable, but we have to have synthesis through some kinds of substrates. And we think geologically, clays and other minerals are a place where we can bring those compounds together. But in some sense, we're still missing a critical step in our understanding of the evolution of life. I don't know if it was a miracle, but we need to figure out how you go from here to here, and maybe Mars will be the place we can do it. This is the fascinating thing, as I'll show you in a second. Now, on Earth, see if this is going to work. No. I got to do this through the hand tool. So this is on the ocean floor. This is a video of a hot smoker, a black smoker, where seawater circulates through the newly formed oceanic crust, and it's through this process that minerals and elements are dissolved and spit out of these belching hot springs. And we think, based on the tree of life, one hypothesis is this was the cauldron in which those ingredients were brought together to create those first organic membranes and kickstart life. And from a detailed geologic point of view, here is a diagram of one of these black smokers as the fluid is circulated through, brought up to the surface. And it's in these little chambers within the boundary between the crust and the ocean that the precursors to life, the organic molecules, were brought together in a compact form that somehow, this is where the miracle theoretically occurs, where it's brought together and life got kick-started. But where can we actually find the evidence for this in the Earth's record? We don't really know for sure. So this is a timeline for Earth's geologic history as we go from the earliest phase, the Hadean, to the present time scale along the bottom. And this is some of the evidence we have of Earth's main events. And the earliest life that we can detect is right around in here. And what I want to point out here is the total amount of exposed rock for the Earth's first billion years. The first billion years of this planet's history would fit into the island of Manhattan. That's about the size of the outcrop. That's not a lot of rock to work with, considering how brutal its life has been. But where was liquid water first stable on the Earth? When did the Earth become habitable and inhabited? And what was the nature of the first inhabitants? We don't know the answer to those questions because the rock record on the Earth has been erased and overwritten so many times. So only such a little piece of the rock record is still there. If, on the other hand, we go to Mars, our geologic timeline matched up against the Earth, Noachian. I love the name of that geologic era, Noah. That was the time of floods on Mars, and the Hesperian, this middle period, and then the most recent period. The nice thing about Mars is 50% of the geologic record from the first billion years is still there. It hasn't been erased. So if you want to trace back and understand the origin of life, scientifically, this is among the most exciting places we can go, which is what's driving our attention. Okay, so when were the first inhabitants? And so in here, if we now place some details about the Martian history up here, what I'm pointing out here is that Mars went through this period of time when they formed lots of clay minerals, which formed in a neutral pH environment. But it went through some gargantuan change in its global environment where it became producing more acidic type minerals, sulfates. So it became more of an acidic planet is one of the hypotheses. So from exploring it for life, we would want to go to this era, this phase of its time. And what type of geologic environments can we look at? Well, I don't think we're going to find tropical rainforests on Mars, but it could be the types of environments where the soil formation or near surface rock-water interaction. It could be in lakes, fossil lakes, or in hydrothermal systems. These are some of the types of places we would like to go see. So how do we find these on the planet from the orbital data? Well, one place that's very interesting and very intriguing is the idea of having fossil or former lake beds that we can detect. Here's an inlet channel forming a delta system and an outlet. And in fact, here on Mars in the Jezero crater, we have an inlet channel coming in here, and it formed this delta deposit in which the colors here, determining from our Mars Reconnaissance Orbiter data, the minerals, and the exciting minerals are these blue and green, because those are the ones that we think could have been the substrates upon which life may have gotten originated. So we can find these from our orbital data, and we have the Earth analogs. This is the Leda Delta in Russia, but we can see these characteristics that we would want to find. So this is the example of seek. I want to find these places, and perhaps I want to rove on these places. And then we want to go to the planet, finding these, and do the in situ. And this is the work that Curiosity is doing very beautifully. Now we're drilling and doing the kind of work of analyzing the in situ side of things. And from those, this is one of the bits of scientific data that comes from Curiosity. I want to point out right in here is the evidence of there being these clay minerals, which is the substrate. So this is really exciting and really good work that's going on from the Curiosity side. Is it enough? We're not sure. We're going to have to actually return those samples to get more of the information. Methane was one of the opportunities that Curiosity provided for us. We can take instruments and check out for the presence of methane. And what it's found with this experiment, the SAM experiment through the use of the tunable laser spectrometer, it was able to determine the gas composition. And at first, they found that there wasn't really detectable methane for a long part of the mission, but they did find at various times that there were these spikes. Why is methane important? Methane is an organic gas that can be produced by biological material, or it can be produced abiotically. But the presence of it is exciting because it can be consumed by microbial communities as well. They're still working on what does it mean for these little spikes of methane, and it will be an ongoing story to figure it out. So from the seek side, on the seek side, I've got this map. There's a global map of Mars. And what we're looking at here is in the different colors are the presence of these outcrops, like I showed you of the delta, which are exciting to go and seek these signs of life. That's a lot, right? How are we going to go see all of them? There's a process that NASA is putting into place where we can try and identify where the next rovers should go to do that work. And one of the areas that I'm very interested in is looking in the subsurface. Because the surface of Mars it has evidence of water, but not a lot. The water didn't exist for a long time. The subsurface, the water was there for at least, it's still there. We've seen this outcrops of water, groundwater spilling onto the surface. So I think in the subsurface, That's where today 50% of the Earth's biosphere is actually in the subsurface, and they live by these very interesting processes of reducing inorganic compounds. The problem is they have low mass density, low productivity, and it's difficult to live there. But what is the record of the deep subsurface biosphere on Mars, and what can that tell us about potentially what's going on Earth? Sorry, what's the Earth's deep biosphere? What does it tell us about what's going on Mars? So this diagram here again has the ages of geologic terrains on Mars, and these I call this kind of it's a Caltech plot, we call it, because you have something versus nothing, right? So these are just the names of different types of deposits we have. And I want to point out that this is the era we want to go after, this blue period, when clays were being formed, water was at work, and it was an exciting, and the pH and other components were in a correct model. So this is where we want to go. We want to be in the alkaline zone, and so we want to look for these types of deposits. Well, and much of this is in the subsurface, and some of these are on the surface. So we have a range of deposits that we could be looking at here. And so where did the alteration occur? So what's the potential among these environments to concentrate and preserve carbon? So this is the range. We want hydrothermal, both in the subsurface and surface. We want deposits related to rivers and lakes, and channels and floodplains. This is where we want to go. So these are the types of environments that would be exciting for us to explore and understand. And I'm going to flip through this. This is the detailed part of the talk. We're looking at the types of clays. This is getting at the mineralogy. If you guys had mineralogy in your time here, we can use the presence in the wavelength of infrared light, reflectance versus wavelength. The presence of these absorptions allows us to detect these minerals. I said I'm going to flip through this because it just shows us that we can use our orbital data to find places on Mars that have the minerals we're interested in. And the idea here, though, is by using the mineralogy and morphology to determine the geologic context, we can define these distinct places we want to go on early Mars. That's the workhorse of NASA and ESA and other nations. So we're doing the seeking. The seeking is doing a great job. We've got an array of potential targets to direct these valuable resources. What's next? So next is Mars 2020 rover. Curiosity rover is doing great stuff. For NASA, the next step is going to be the Mars 2020 rover, which is going to be the next leap to seek signs of life, to do rigorous in situ science through the use of the instruments selected for this rover. And it's going to create a returnable cache of samples, and it's going to do in situ resource utilization experiment. Michael Hecht, I think, talked to you guys earlier this week, and that's a very exciting experiment, and I'm hoping that it's going to work great on its process there because it cuts the cord, so to speak, for exploration. Now, this is one of the parts about where to put that lovely, fantastic rover, which is being built today. Where are we going to put it? And these are the criteria that the community, NASA and the science community is using. We want to have the presence of subaqueous sediments. So that's a big word to say sedimentary deposits that were in lakes or oceans, for example. Or hydrothermal sediments. So that would be like if anyone's been to Yellowstone hot springs, it's those tufa deposits or travertine deposits. That's a hydrothermal sediment. Or rocks that were altered by hot rock. That's the second priority. We want to see the presence of minerals indicative of this clay, carbonate, and sulfate. And they have to be in the rock itself. And we want to go to this early period, right? I kept harping on it. It's the early period. It's the early period. And that's where we want to go. There are some other criteria to look at the igneous rocks to understand. And down here at the bottom, it cannot be a special region. We don't want to go to those really exciting recurrent slope lineae. Those appear to be groundwater outcropping on the surface because we just don't know if that would do forward or backward contamination and other, that's the planetary protection side. So here, is a map of the landing sites that are under consideration. And this February, there will be a workshop which you can all attend. It's open. You're welcome to come. It'll be in Pasadena to look at, to take these 8 landing sites that have been proposed and evaluated by the scientific community. And there's the location on Mars where they exist. You can get this on the Mars 2020 landing site. You can see all these. And what we're looking at here is it is restricted in latitude between these 2 lines, and it's restricted in elevation. You cannot go to the black areas. And so at the moment, they've got these 8 sites, and there'll be a detailed discussion and an evaluation of what they might be. 5? Good, I'm wrapping up. And so I'm going to put this complicated diagram up here, but just to simplify it, we have time along this top here, geologic eras along here, mineral history along here. This is where we want to go. Many within the scientific community, that was the criteria that said Noachian or early Hesperian. This is where we want to go, Noachian and early Hesperian, because this is when there was lots of activity going on hydrothermally, water on the planet. There was surface water that we know to exist, and it was an exciting time for Mars's history. So that is where we hope to go. Sorry, I finished off there. Let me bring that back up as the last. I'll put that up, and then I'll we'll say, so just to sum up there, that's going to pop up, and we'll just flip through. So hopefully I talked to you today about the geologic, some of the key geologic aspects of the Martian environment that are driving the thought process within the scientific community about where we might want to focus our attention in the seeking out signs of life. I want to thank you for your attention. I hope you guys are having a great meeting. It's been wonderful to be here, and I'm happy to take any questions. Thank you.